In this lecture, I'm going to write down some Boolean expressions and then solve them with you. First Boolean expression. It is A and B and inverted C, all inverted. I see this big inversion sign here and I think De Morgan. De Morgan lets me break up that sign. As long as I keep everything the same under it, but I change the sign. Then now I can break up that inversion on the outside. So that was theorem number 17 that I used in this row. Now I see that there's two inverted bars of equal length over the C, and that's theorem 18. And that's the answer. Let's look at another question. Let's do A and inverted B plus C, all inverted. In this case, again, I look to De Morgan's to break up that inversion sign. One of my factors is AB bar, and one of my terms is AB bar, and the other term is C. I need to change the sign in between those, then I can break up this sign. And that was theorem 16. Now I see that I have this large bar here. So I'm going to use De Morgan's again, but this time theorem 17. I'm going to break up the A, B bar, but I'm going to change the sign, and that lets me change the big inversion to two small inversions before it. But I have to be careful to have some brackets because all of that is ANDed with C inverted. And now I see that I can use this was theorem 17. I used theorem 17 to get there. And now I'm going to use theorem 18 to get here because I have a double inversion on B, which of course just inverts and then inverts again, which is just the original function. And now I can distribute across, keeping in alphabetical order. And this is my answer. So I distributed using, I believe that's 13A. And then that's our final answer. So let's do another example. Let's do the larger example. Here I have two terms with three factors in each term. I'm going to first use De Morgan 16, theorem 16, and I'm going to write down each of those terms. There's the terms as they exist. I need to change the sign. The sign used to be an or, now it's going to be an and. I should carry some brackets there. And now I get to break up this big long bar into two bars, one over each set of terms. And those terms have now become factors, mathematically speaking. So now I'm going to use De Morgan's again, but this time it is number 17. And I'm going to use 17 twice, one for this and one for this. So here I am using 17. So I'm going to write down the same inputs that I had under this big orange bar, but I'm going to change the sign. That lets me break up. I'll do that in orange. Lets me break up that bar. And again, same with the other one. And you can put the and symbol in between, or you don't have to. You can just use brackets for that. X, Y, Z. These ones were inverted. Used to be ands, now they're ors because that's what De Morgan says. Allows me to break up that big orange bar. And now I'm going to recognize that I have a lot of inversion signs that are inverted and then inverted again. So that's theorem 18. Remember 18 says a bar bar equals a. So this becomes x plus y bar plus z, anded with x plus y plus z bar, I believe. Now the next thing I have to do is I need to distribute. So I use a different color. So that means x times x plus x times y plus xz bar plus y bar x, etc. So distributing, what is that called? That is 13a, theorem 13a. And again, have your midterm formula sheet in front of you to look at that. So I'm just going to go through that. X plus x, y. I'll just be quiet as I go through it. And I'm staying in alphabetical order. So I just performed 13a, theorem 13a, and hopefully did that correctly. Now I can, a few theorems jump out at me here. Let's look at Z bar. Z bar must equal 0. That's theorem 4. And you really have to understand why Z bar equals 0. It's because it's an AND gate. And if one of them is inverted and one of them isn't, then one of them must be 0. And is only going to be a 1. If both of them are 1, clearly one of them is 0. Therefore, the result is 0. So theorem 4 gives me that. And then I also have a y bar. That must go to 0 as well. And we also know, let's see, x and x, the answer must be x. And that is theorem, that is theorem 3. It's theorem 3. And any more opportunities in there? I think that's all the opportunities that I have to use some theorems on this line. Simplifies it a little bit. Now I can factor here. I see that x exists in a lot of these terms. So if I want to, I can factor out the x. It's not essential though. It's debatable which form is more simplified. All right, and that's the final answer. And I used a theorem. I think we do have a theorem that basically lets us factor. It's basically, I use 13a again backwards in the opposite direction. So those have been 3 examples of simplifying Boolean expressions.